Hey, it's Dr. J. I'm back with another lecture on limits at infinity. We'll call this one part 2. So when we left off last time, I was showing you how to calculate limits at infinity and also at negative infinity using algebraic techniques. I'm going to summarize that again today, and then I'll show you some other additional techniques that'll help us get a better idea of the overall behavior of the graph, and we're going to get more into detail with the asymptotes. So I don't really have a big backstory. I don't have a lot of theorems or anything today. Let's just get right into an example, kind of right where we left off last time. So we start with a rational function, which is the ratio of two polynomials. The numerator is a degree 1 polynomial, also known as a line or a linear function. And the denominator looks like a quadratic polynomial. So we've got two directions to go. Okay, we've got the limit as x goes to infinity, and we also have the limit as x goes to negative infinity. Now, the first thing I'll mention with a rational function is this is not true for all functions. For example, in the first part of this video, we saw polynomials where one limit could go up to positive infinity and one limit could go down to negative infinity. And that's not true with rational functions. Rational functions are the ratio, it's a fraction, of two polynomials. And once you know one of the limits, you get the other one generally for free, if the limit exists. All right, so I will mention that. Now, if the limit does not exist, then we might need to dig into it a little bit more. But let's just get right into it. So the technique is to divide everybody by the largest power of x. So the largest power is x squared. So we're going to divide everybody by x squared. I am skipping a lot of the arithmetic. I will just briefly explain what I just did. So I divided 8x divided by x squared. So that'll be 8 over x. I divided 8 divided by x squared. That'll just be 8 over x squared. I divided 4x squared divided by x squared. So that just becomes 4, and so on and so on. So 7x divided by x squared is just 7 over x. And then negative 3 divided by x squared is just negative 3 over x squared. All right. In the first part of the video, I showed all of the steps, and it took up a lot of space. So I'm skipping that and jumping right to it. All right, so now as x gets very large, we do have a theorem that we learned in the first part. A constant divided by x to any power larger than 1. So this is first power, second power, so on and so forth, will always approach 0. The limit will be 0. Now this one is a constant, so the limit of a constant is just a constant. That's 4, and then these limits are both 0. So the limit is 0 over 4, which is equal to 0. So the limit exists. It's equal to 0. That means that when I do the other limit, so if the limit as x goes to infinity of f of x is equal to L, and f of x is a rational function, I don't have a lot of theorems today, but I mean, this is technically a theorem. It's a little baby theorem. All right. Now, it does have to equal a limit, like, the original definition that I gave. So L has to be a number. So this is your L. All right. This theorem is not true if this limit does not exist. So f has to be a rational function. That comes from the word ratio. It's the ratio of two polynomials. Then the limit as x approaches negative infinity is also L. So this is a buy one, get one free. This is the symbol for therefore. 3 dots, dot, dot, dot. The limit as x approaches negative infinity of this function, I'm using the same function, is also 0. All right. In other words, you don't have to do all of this algebra again. I mean, unless you want to. It's really not too terribly complicated. If you replace infinity with negative infinity, this is still going to be 0. This is still going to be 0. This is still going to be 0, 0. You get all 4 of these zeros. This is still going to be 4. Yeah. And so you're still going to get the same limit. All right. So the key is that this is a rational function. All right. So that was just a very quick warm-up example 1 of what we kind of left off doing in the last one. And there is a horizontal asymptote. So this is a continuation of this theorem. At y equals L. All right. So it's a horizontal asymptote, so it's an equation y equals L. All right. So in this example, the HA, we'll abbreviate it HA, is y equals 0. That would be the equation of the horizontal asymptote. Intuitively, I'm not going to take a lot of time drawing the graph in this example. I'm going to wait for a more exciting example. But intuitively, it would be a dotted line right on the x-axis. Yeah, so when y is equal to 0, you are on the x-axis. Let's try another one. So 2x squared minus 2x plus 6 over 5x squared plus 8x plus 3. All right. By the way, you could start with negative infinity if you like. Doesn't really matter. Sometimes I start with positive infinity. Sometimes I start with negative infinity. It really doesn't matter because if one of these exists, then the other one also exists and is equal to the same value. So I'm starting with negative infinity this time. Dividing everybody by x squared. Right? That's the largest power of x. So you're going to get 2 plus 2 over x plus 6 over x squared, and then 5 plus 8 over x plus 3 over x squared. This is where the algebra, mental math algebra really comes in handy. Again, all of these terms are being individually divided by x squared, doing that in my head, and then writing out the result. You will notice a very distinct pattern. Yeah, the largest powers are both x squared, so that's how you get the 2/5. All of these guys are going to go to 0 because they all have an x in the denominator. I got to get my signs right, but it really doesn't matter. I almost screwed that up, but it's -2 divided by x, which is still going to be 0. So we'll just make sure that I match. You're subtracting 0. All right. The denominator, it's all adding, so plus 0 plus 0, so the limit is 2/5. If we were doing this the way we did at the beginning of the course, I just keep making it worse, you would get a decimal. Remember at the beginning of the course when we first were exploring using the calculator, hammering out a bunch of numbers, right? Why did I write 2/4? 2/5. So if you did this on a calculator, you would get 0.4, right? That's what the decimal would be. I like algebra because it gives you a nice exact number. It's either going to be a fraction or a whole number or some kind of an integer. It's going to be not a decimal, typically. You could write it as a decimal, but I'm not going to. It's 2/5. All right, and then again, we have this sort of, baby theorem. I call it the BOGO theorem. I do lots of BOGOs in this class. Buy one, get one. Yeah. So oftentimes in this course, there'll be two questions in which you really don't have to solve them both. You could just solve one and you get the other one for free. So if you know one, you automatically know the other. Okay, they do have to exist. Okay. So we'll say BOGO. You don't have to say that, but I'll say that. Buy one, get one. The limit as x goes to positive infinity is also 2/5. And there is a horizontal asymptote y equals 2/5. All right. Be careful. Limits are just numbers. 2/5. Now, the asymptote is an equation, y equals 2/5. All right. I also want to point something out that's sort of I've kind of been leading us down this road the last couple videos by pointing out that the limit equals 2/5, but it never actually touches 2/5. Right? It doesn't actually hit 2/5. It just gets closer and closer and closer. All right. So, in previous sections, I might have said, well, it approaches 2/5. I mean, it really is, right? And I'm considering making a separate philosophy video about the difference between approaching something versus equaling something. At this point, I'm just going to say that if you calculate a limit and you get a real number, you can say it equals it, even though it never actually equals that real number. Right? It would get on a calculator, it would never actually be 0.4. It would be 0.3999999 and 0.39999999999, right? Or possibly 4.01. Or 0.41. Sorry. 0.401, 0.40001, right? It'd be very, very close to the fraction 2/5, but never actually hitting it. But we still say that the limit equals that number. The limit equals that number. Remember, infinity is not actually a point, or negative infinity. Neither of these are actually points. So philosophically, we could have a whole other discussion about whether this actually exists or not. Well, the limit exists, but there's no dot. It's a tendency. We're saying the limit is approaching that. All right. I know I insist upon myself sometimes. Okay. So that's how we do horizontal asymptotes. We've also seen vertical asymptotes, which means something completely different. I'll slow down a little bit and go back to some very basic problems. Something we might have seen in the previous video. So if you take a limit to infinity or a limit towards negative infinity, you get a horizontal asymptote. To find a vertical asymptote, it must be the limit as x approaches c equals some constant divided by 0. Little notational blurb. This c is a constant. This c is a different constant. So I sometimes will say k over 0. I know previously I might have used c for constant, but if I've already used a c on the board, then I can't use it twice. I'll use k for the other version of constant. So this would be dne. You would say the limit does not exist, right? The limit does not exist, and there's a vertical asymptote. Let me write out the whole word for you so you get the spelling. Typically, I just say VA. Asymptote. Yeah. At x equals c. All right. Typically, what is c? C is the number that causes the denominator to equal 0. All right. So look at this example here. 4x minus 8. So look here. And you could probably guess where we're going to take the limit. We're going to take the limit as x approaches 2. Yeah? Because 4 times 2 is 8, and 8 minus 8 is 0. So our c is going to be 2. All right, let's go ahead and do that limit. 12 times 2 plus 11 over 4 times 2 minus 8. Notice this is not a limit at infinity. This is a limit approaching 2. I could get more into the details later in this lesson about whether I'm approaching it from the left or whether I'm approaching it from the right. At this point, I'm not being precise about what side I'm on. I'm just saying I'm approaching 2 generally. So we're getting very close to 2. I can just directly substitute in the 2. And you'll see that you get 35 over 0, which is dne. So this limit does not exist. All right. You do have to get a constant in the numerator other than 0. All right. So you do have to verify that the numerator is not also 0. That would be a different case, which we'll get to later. So when I say k, I mean something other than 0. I think I might have called it L before. I mean, the one thing that we are notoriously consistent is with our inconsistencies of what we call f. And sometimes I'll call this capital F and capital G and lowercase f. And it's just a function, and that's just a constant. And let's not make a huge deal about it. So there is a vertical asymptote. I'm going to now abbreviate VA, vertical asymptote, at x equals 2. All right. I might actually draw this one, yeah, because it's relatively simple. I can show you how much faster it will be to draw than the one that I did previously. All right, so that's how we do vertical asymptotes. You look for the number that causes the denominator to be 0. That would be where we take the limit. That limit will not exist. It will be dne, and then there'll be a vertical asymptote. So to find the HA, horizontal asymptote, take the limit as x approaches infinity Yeah, or the limit as x approaches negative infinity. All right. It's your choice. If either one of these things exist, they're going to be equal to each other, so you don't have to do them both. One is good enough. I might ask for both, but one of them is good enough. All right, this one is, they're both linear, the first degree, so we're just going to divide everybody by x. Both of these fractions go to 0. And I wonder if you're noticing a pattern. You see, 12 divided by 4 comes out to be 3. Now, I do have to make sure that those are actually constants when you simplify it. All right. So sometimes your brain might see a pattern. 12 divided by 4 is 3. Sure, that's true in this case. But there are other examples where that could be a 12 and that could be a 4. If the rest of the terms were lined up, had different powers and such. And again, we've got a long way to go in this lesson still. So I might point out when that pattern is true. I recommend doing it mathematically, and then if you notice a pattern, kind of put a pin in it and see if that pattern holds up. See if it holds up in every example. So there's a horizontal asymptote, y equals 3. So let's make sure that you see that these things are distinct. All right, this one's a dotted line that goes horizontally, and this one's a dotted line that goes vertically. All right. Let's see the graph. All right, let's see the graph. So I've got a horizontal asymptote at 3. Passes through the y-axis at 3 horizontally. I've got a vertical asymptote at, let's take a peek, 2. One, 2. All right. And now I need to plot a couple points. Now on the homework, you really only need 1 point. All right. The homework is very sort of automated. You just use your mouse. All right. So on the homework, click right here. So 1 point to get the asymptotes to stick. Don't click at 3 and then also click at 2. Just click it 1 time right where 3 and 2 intersect with each other. So y is 3 and x is 2. All right. X is the vertical asymptote. Passes through the x-axis. That's why we say x is 2. And y is the horizontal asymptote at 3 because it passes through the y-axis. All right. All right, so now you need 1 additional point. I actually like to do 2, but on the homework, you only need to do 1. So just plug in any number besides 2, right? You can't plug 2 in because it's an asymptote. So I usually just plug in 3 or 1 or something like that. How about 1? X equals 1. So we'll plug in 1. This is called evaluating. This is to get our additional point. So 12 times 1 plus 11 over 4 times 1 minus 8. I regret my choice now. 4 minus 8 33 over negative 2, which is, over negative 4, sorry. So the top is, it's not 33, sorry. God, I should really use my calculator. It's 23 over negative 4. You could divide that out if you like. It's negative 5.75. The graphing is not that precise, so you can just put it. So 1, 2, 3, 4, 5, 6. The computer will accept it anywhere between negative 5 and negative 6. So just put a dot right there. As long as the tolerance is within 1 unit, so it has to be between the correct units. I was actually hoping it would be negative 5.5. It would be exactly in the middle. All right. Just the value that I wrote down didn't turn out as nice as I had hoped. But this actually tells you something interesting about the graph. There's an asymptote, and the point is negative, and I called this a sample point. It tells you that the limit as x approaches 2 from the left is negative infinity. So it's telling me that the graph is going down towards negative infinity. I'm just going to kind of fake it. Once you click on that dot, the computer will automatically populate the rest of the curve. I'm not being very precise. I don't know really where it crosses. I mean, I could be very, very precise, but I'm not going to. All right. So here's the thing about the computer. You just have to make sure that the arrow is pointing in the right direction, and then it'll automatically populate the other side as well. And I've done a lot of modifications with this online software that you have. I've done a lot of customization for this course and other courses that I teach as well, but especially calculus, where I customize the questions specifically for you. But they're not all perfect. I wish as an instructor that it would, make the student come up here and click again to get the other half, but it doesn't. These are kind of like mirror images of each other. You can think of them like twins. And so as soon as you plot one of them, the other one, it's another one of those BOGOs, buy one, get one. I will plot another point, though, just for fun. I just want to confirm that that's true. Let's do 3 or 4. I don't know. I'm going to do 4. What the hell? So I'm going to get 12 times 4 minus 11 over 4 times 4 minus 8. So that's 48 minus 11. Oh, it's not minus 11. Plus 11. 16 minus 8. So that's 59 over 8. I'm just tired of approximating. So it's going to be... what is that? That's 7 3/8. Yeah. Or as a decimal, 7.375. Again, as long as you're somewhere between 7 and 8. So 4, 5, 6, 7, 8. As long as it's somewhere between there, it would accept it. I hope that that's clear to you. The main point of this is the calculus here, so I want to now discuss the limit. I really don't care what that number is. Okay, you can use any number you like. I mean, you do have to have a point that's valid. You can even go fishing, right? You can just keep plugging in numbers until you get a nice solid number. I hate to use that word, but it's kind of grown on me after a while. Right? I don't feel like fishing right now. I just take my first pick, and whatever I get, I make it work. But if you're not happy with it, or for some reason the computer is not accepting it, just keep fishing until you find a whole number. I made most of the questions pretty easy to catch a fish. Yeah. But now remember, this is a calculus course, so I'm going to be asking you calculus questions. So I've already done the limit on the left, so let's do the limit on the right. And what I meant when I said I don't care what that decimal was, sorry, I erased it. It was f of 4 was 7.375, right? What I meant is I don't care that that's 7.375. All I care is that it's positive, yeah, and it's approaching the asymptote. As soon as it comes out positive, as long as it's near the asymptote, all right? You wouldn't want to pick a number far away from the asymptote. You want to stay near x equals 2. 3 probably would have been a better choice, but I think it would have been off the screen. So I chose 4 instead. All right. I'm trying to make it fit on the grid that I have here without having to adjust my scale. All right. So again, we know this limit doesn't exist, but we can, by looking at the graph, analyze the left and the right behaviors of the function. All right. So back to that pattern. I want you to get the right answer, because I'm your teacher, and I want you to be successful. So I do want you to get the right answer, but I also want you to explore a little bit about different possibilities and different ways of calculating the results. And I want you to resist the urge to just Google the answer. I sometimes plant these problems that are very intuitive and sometimes not always straightforward. The Google might not have a straightforward answer, so I'm trying to get you to stay human and use your mind and use your knowledge to find these answers. But I also want you to have options, right? I'm a big fan of options and being able to say, well, sometimes I like to do it this way and sometimes I like to do it that way. It really helps build your mathematical maturity. It's going to help you become a truly educated person and not always do something exactly the same way. So I've done a lot of these examples the same way, but you might notice a pattern. All right, you might. So if you're taking the limit of two polynomials, we'll call those A's, we'll call these B's. So A for numerator, B for denominator. All right. The subscripts indicate the index or the coefficient of what term it is. So a subscript of 0 means it's a constant term. I sometimes use K or C for constants. I'm using a subscript. The 0 means constant. All right. The 0 literally means it does not have a variable with a power. Right? Well, it does have a power. It's a power of 0. You just don't see it. And then the 1 means that it has a variable with a power of 1. The 2 means it has a variable with a power of 2, and so on and so forth. The ... would represent, 3, 4, 5, all the other powers. All right. Quite often in this class, you don't even have much higher than 2. Right? We're not building a rocket ship in this class, right? It's business calculus. We're going to be getting to some application problems very soon. I'm trying to really finish this foundational stuff. We have to know enough to be able to, start spending our money. But as the powers get larger, you just use letters like N and M. All right. And there are 3 possibilities for the limit. Number 1, if n is greater than m. Yeah. So if the numerator is greater than the denominator, then the limit does not exist. Yeah, we've already seen that in part 1. We'll see it again today, right? But I want you to see this pattern so that as soon as you see the problem, when I ask you for the limit, oh, by the way, it's the limit as x goes to infinity or negative infinity. Yeah, again, I'm doing the BOGO, so once you know one, you know the other. Right? The limit does not exist. All right. We may want to explore a little deeper. For example, we know it doesn't exist, but where is it going? Is it going up? Is it going down? Negative infinity, positive infinity. We might want to explore the behavior a little bit more. All right, but for a quick answer, you could just say it doesn't exist. That's the quick answer. All right, that's the easy one. If n is equal to m, so we saw one of these today, if they're both 2, like for example, if it looked like this, right? They're both second power. And then these terms don't exist. We saw that one. It's very simple. The limit is an over bn. Yeah, it exists. I'm happy about that. That's my happy face. And not only does it exist, but it's a very nice number, right? 4 divided by 8, or 16 divided by 2, or negative 1 divided by 3, or whatever it comes out to be. Yeah. And then finally, the third case is if n is less than m. So n would be, I don't know, 2, and then m could be like 3, yeah? Or n, the top could just be 1, that's the one we just did, and then the bottom could be 2. So anytime the top power is smaller than the bottom power, it's interesting, n is numerator, but m is denominator. Could use d for denominator. I use m, denominator, m, yeah. Then the limit is 0. And it also exists. All right. Take away my happy face, because my happy face looks like a 0. All right. Sometimes I put a little happy face in my 0. All right. So it's either going to be does not exist, right? Top is bigger than the bottom. Degree. We're talking about the degree. All right. If the degrees are the same, then it's just a fraction. Sometimes it comes out to be a whole number, but I mean, you have to divide it to see. Yeah. Or if the bottom is bigger than the top, so bottom is n, m, top is n, then you get 0. Nice. Nice simple pattern. That means we could fly through the rest of these examples. Well, we could fly through this part of the example. I'm doing that because there's going to be a lot more work that I don't necessarily want to fly through, but I would like us to be able to fly through this one. So 10x squared plus x plus 11 over 2x squared minus 28x plus 98. All right, before I erase this, let's decide which possibility it is. So this is your n, and this is your m, and they are clearly the same. Yeah, they're both 2. So that means we are in this case right here. Yeah. an and am, or bn, a over b. You could just say a over b, really. The N and the M don't really matter. The top is supposed to be N, the bottom is supposed to be M. All right. Although you don't really need them in your notes. You could just say A over B. So A is the leading on the top, B is the leading on the bottom. So the limit as x goes to infinity of f of x is 10 over 2, which is 5. All right. Using the buy one, get one free deal, the other limit is also the same. Two for the price of one. There's a horizontal asymptote at y equals 5. All right. That's a lot easier than dividing these all out. If you're watching this video and you haven't finished some of the previous problems, I recommend knowing the technique, because that technique will become important. I didn't teach it just to give you something to do. That the algebraic technique is an important skill, but it's also important to know when you can predict the result without using the technique, right? You do this all the time in life, right? I mean, if I ask you what's 9 times 7, right? You know it's 63. Right? 9 times 7 is 63. You don't need a calculator. Yeah? You don't need, but you know that if you didn't know what 9 times 7 was, you have a method for figuring it out. Right? You probably have several methods. You could use a machine. You could use your fingers. You could use long multiplication, 7 times 9, and actually multiply it all out on paper. I mean, there's several different techniques. And that's really sort of the core of my philosophy when it comes to teaching and also, doing mathematics. All right, so that's our horizontal asymptote. Now we want to know the VA. All right, it's not quite as easy because we want to look at the bottom. Don't really worry about the top so much. Not yet, anyway. But look at the bottom, the denominator, and try to factor it. So I notice that everybody is divisible by 2, so I could factor out a 2. I want to try to find the number or numbers that make the denominator 0. I'm not really worried about the numerator yet. I'll get to that later. Most of your attention should be on the denominator. 7 times 7 is 49. They should both be negatives so that you get a positive 49. And if you add the two negatives, you get a negative 14. So this is the simplified version of your function. All right. Well, actually, it's not simplified. I mean, it looks simpler, but it's factored. The factored version of the function. You want to be able to do that so that you can solve for the VA. Yeah. The VA, you want to look here in the denominator and ask yourself what number would cause that to be 0. And I hope it's clear that 7 would cause that to be 0. It's essentially the opposite of whatever is in the factor. Right? So if this would have been x plus 3, then it would be negative 3. Yeah, if it was x minus 7, well, it's positive 7. Because if you tried to plug in 7, right, you would get 10 times 7 squared plus 7 plus 11 over 2 times 7 minus 7. Sorry, I'll rewrite that in a second. You'd get 10 times 49 plus 18 over 2 times 0. So I would get 0 in the bottom. Now I should double check that I don't get 0 in the top. You get 490 plus 18, 508 divided by 0. That's DNE. There's the K I was talking about, the constant. So you have a constant divided by 0. And so that's DNE. All right. So we get so there is a VA, vertical asymptote, at x equals 7. All right. So if you plug in 7 and you get 0 in the denominator, but some non-zero constant in the numerator, that does not exist, and you get the vertical asymptote. All right, that's it. So the two answers are the horizontal asymptote and the vertical asymptote. We also have a couple limits here that we calculated. Before I erase this, I should also mention the limit. Note the limit as x approaches 7 is also DNE. Right. That's what I did here. When I tried to plug in 7, I'm evaluating it. I get 0 in the denominator. That tells me that the limit does not exist. So I'm just trying to summarize all the different parts of this question. All right. Well, the last thing we're going to talk about in this video, and I've got a few examples to show you this last topic. It's a little more tricky, a little bit more technical, would be if you got 0 over 0. Right? We spent some time talking about that previously, and I want to dive a little deeper into that concept. I want to revisit the techniques for resolving those limits if you get 0 over 0, what that means. So example 5. X plus 6 over x squared plus 8x plus 12. All right. Okay, so what happens? Let's do the limit as x approaches -6. Because that causes 0 in the numerator. So I'm trying to force the issue. I want to end up with 0 over 0. It also causes 0 in the denominator. Now you might not notice that right away, but I kind of gave it away in my preamble here. That I'm trying to force it to be 0 over 0 so that we can learn the next technique. So I'm particularly crafted this one. So this is 36 minus 48 plus 12, which is -12 plus 12, which is 0 over 0. That's what we call the indeterminate form. So we don't know. It could be infinity, it could be negative infinity, it could be DNE. That's really what we mean when we say infinity and negative. I mean, that number doesn't exist. It could be a number. Right? Could be 0. I mean, there's lots of different possibilities. Or there are a few possibilities, I guess. All right, so how do we do that? Well, we're going to do the same thing we did in the last example. We're going to simplify this by factoring it. Now the numerator is already, factored. There's nothing to do in the numerator. If there was more stuff in the numerator, I would work on that as well. The denominator can be factored. I'll tell you what, for memory's sake, if you get 0 over 0, that means one of the factors will match. You'll get a matching factor. So this time it's x plus 6 and x plus 2. Again, I'm not teaching a whole lesson on factoring, but 6 times 2 is 12, and 6 plus 2 is 8. That's your quick algebra review. All right, and then that gives us a simplified form of 1 over x plus 2. Remember, there's an invisible 1 right here. It's technically 1 times x plus 6. When you cancel the x plus 6, you better put that 1 right there. And so the limit as x approaches negative 6 of 1 over x plus 2 is equal to 1 over negative 6 plus 2, which is 1 over negative 4. Yeah, or you could just say negative 1/4. Yeah, or you could say negative 0.25. I like exact numbers whenever possible. All right. So what does this mean? All right. What does this mean? This means that there is a hole in the graph at negative 6. So you want to use the value from the limit. These should be the same value, negative 6. And then this is your y value. There's a hole. The official name of this is a removable singularity. Or a removable, I'll use the language that we have in our book, discontinuity. Singularity means it's a single point. Discontinuity means it's a break. So this is the language that I'm using. You'll sometimes hear me say singularity, but I'm going to write a removable discontinuity. In other words, a hole in the graph. All right. And then, if any factor remains in the denominator, take another limit. So this time we're going to go negative 2. So this factor remains in the denominator after we simplified it. We're going to take another limit, and we're going to get 1 over negative 2 plus 2, which is 1 over 0, which is dne. Now, if this factor wasn't here, then I wouldn't do this part. Right? So, but when I simplified it, I simplified the x plus 6, and I have this remaining, this x plus 2 remaining. This is like my simplified version of the function. Right. Now I can take another limit, and that's going to give me an asymptote. So we have a vertical asymptote, x equals negative 2. So notice the hole represents the limit as x goes to negative 6. Because you get a number. Yeah. So that creates a hole in the graph. Let's do a few more of these. There are basically 4 things that I'm asking. I'm asking for these 2 limits, one of them at negative 6, approaching negative 6, the other one approaching negative 2, and then I'm asking for the asymptote. Negative 2 is the asymptote, because that's the one that's dne, right? And then the one that exists, negative 1/4, that becomes the hole, the removable discontinuity. Let's put it all together and do another example with everything we've learned today. everything we've learned today. Negative 2x squared plus 12x minus 16 over x minus 5. This time it's the denominator that does not need to be factored. All right, so there's a couple things I want to ask. What is the limit as x approaches 5? Let's see. Negative 2 times 5 squared plus 12 times 5 minus 16 over 5 minus 5. So I know I got a 0 in the bottom, the denominator. Let's see what happens in the top. Negative 50 plus 60 minus 16. That's going to be negative 6 over 0, which is dne. All right. It's not 0 over 0. Why do I want to check that first? Because if it's not 0 over 0, then I don't really need to bother factoring this thing. Yeah. At least not yet. I know that it's dne. Yeah. I could try to factor it. I mean, I did that last time. So I factored out a negative 2 from the top, double checking all my signs. When you pull out the negative, it changes the positive to a negative and the negative to a positive. I like to put parentheses around everybody. Let's see, x minus 2, x minus 4. And so there are no matching factors. No canceling factors. All right. I always wonder if canceling has 2 L's. I don't know. It doesn't really matter. None of them matches. There's no match on the top and the bottom. So that means there's no hole. Removable discontinuity is dne. Yeah, I don't get any canceling. All right. The vertical asymptote, because I got negative 6 divided by 0, the vertical asymptote is 5. X equals 5. All right. And then the horizontal asymptote, well, let's use the rule. Yeah. The numerator has a power of 2. The denominator has a power of 1. So it's also dne. The horizontal asymptote does not exist. Now, I mentioned this earlier. I want to put a little sort of asterisk here. All right. It requires some more study. Because the horizontal asymptote does not exist, that means that the limit as x approaches infinity of f of x is dne, right? Well, yes, it does. It really does. However, as I mentioned earlier, we're taking limits at infinity. All right, and we want to know what's happening to this function. Right? I want to know the behavior. Telling me it doesn't exist it's correct. I mean, it's true that it doesn't exist, but I want more detail. Than simply not existing. All right? I want to know, for example, does it go up? Does it go down? Which way is it going? Yeah. I guess there's really only two possibilities. It's either going to go up or it's going to go down. Right? So this is where we abuse the symbol equals, right? Starting right about here. And we'll probably continue to abuse it for the rest of the semester. All right. The technical answer is it does not exist. However, if we're asked for more detail, all right, I want to know more than that, then I'm going to use an equal sign, and I'm going to say it equals something that it really doesn't exist. But that's the whole concept of infinity, right? We know that infinity is not a number, but it's a symbol. So I can put down the correct symbol. Is it infinity or is it negative infinity? All right. It's just a little more detailed answer than simply saying it doesn't exist. We typically only do this in the case where the asymptotes don't exist. The horizontal asymptote doesn't exist. I wouldn't be asking this in this way if the asymptote existed, because you would already know the answer. You would just tell me it's equal to 0 or it's equal to 1/2 or something. All right. So let me get into it. All right. Remember how we factored this thing. I just erased it, but I wish I didn't. I get negative, what was it, x minus 2 and x minus 4 over x minus 5. All right. Just plug in a big number for x. And you don't really have to go very big. You could even do 100 if you really want. It doesn't really have to be very big. You can use the original or you can use the factored form, but I'll show you why the factored form is super easy. Look at how easy it is to plug in a big number. 100 minus 2, 98. 100 minus 4, 96. 100 minus 5, 95. Yeah. And then ask yourself, what is f of 100? I don't care what it is. Yeah. If you want to do it on your calculator, you can. Here, let's do it one time. And I'll never do this again. Negative 2 times 98 times 96 divided by 95 equals negative 198.0631579, blah, 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 blah. Do I care? Please tell me I don't care. I don't care that it's 198. All I care is that it's negative. Yeah. So if I would have done 1,000, then this would probably be 1,980. I didn't do it, so don't believe me. But in other words, it's just another big, I'm using the word big in quotes, negative number. So I know that this limit is negative infinity. Right? And again, technically it's DNE, but it tells me that it goes down. The arrow points down. Similarly, the limit as x goes to negative infinity of f of x plug in negative 100. I just want to remind myself that it was x minus 2, x minus 4, was it 4? Yeah, and x minus 5. Just reminding myself of what the factors are. I mean, if you're not good at factoring, or if you find that you don't want to spend the extra time factoring it, you can actually do this problem without factoring. You would just have to use the original version of the problem to do this. I just find it easier to use this version. So you get negative 2 times negative 102 times negative 104 over negative 105. And this is a positive number. And again, I told you I wasn't going to do it on the calculator, so I'm not. But trust me, -2 times -102 times -104, all divided by -105. All of the negatives are going to cancel out. You're going to get a big positive number. And so that goes to positive infinity. And my final note is this is detailed infinite behavior for a limit for limits that do not exist. All right. So again, would I accept DNE? Well, sometimes, yeah, if I'm not asking for more specific behavior, because technically these are both DNE. But when I'm asking for detailed behavior about the graph, again, we call this the end behavior. I'd like to know, well, this arrow goes down and this arrow goes up. Because at some point, I'm going to be drawing graphs. That might be in part 3, because I've already gone over an hour here. But I'm going to do 1 more, maybe 2. See how time will tell. All right. To summarize the answer, because it's been a while, I should make sure that I tell you the HA was DNE. There really is no detailed information about that, because there is no horizontal asymptote. But there was a VA. It was x equals 5. And so if I drew a graph, at 5, I'm not doing a very detailed graph. It would look like that at x equals 5. All right. As you go to infinity, the graph would go down to negative infinity. There's no horizontal asymptote. Yeah. And as you go to negative infinity, the graph would go up. So that's roughly what the graph looks like. It looks like 2 curves with a dotted line between them. On the left-hand side, the arrow is pointing up, sort of up and to the left. On the right-hand side, the graph is pointing down and to the right, and it never levels off. Right? So this graph just goes like this, all the way to infinity. That's what this means. I don't have time to plot a bunch of points and do this, and we don't have the sophistication to do much more detail than that right now. Just wanted to throw that out there before I move on to possibly the last example, looking at my clock. I should probably never look at when I'm teaching. All right, so what do we got next? Example 7. Oh, this is one of my favorites. I love this one. So nice and compact. Yeah. Let's find some limits. Let's do 4. And -4. All right. Why 4 and -4? Well, because the denominator has that classic algebra factorization of perfect square of 16 would be -4 times +4. Yeah, because the negative times a positive will give you that -16. So we're going to simplify this to 1 over x plus 4, and this is what we're actually going to take the limit of. Now that we've seen the technique, it requires a lot less work, especially with one that's nicely factorable like this. The trick is you need to know what to do before you take the limit. All right? And I'll talk a little bit more about if I would have tried that sooner, what would have happened. Right? But for now, I know that I get 1/8. All right. And then for this limit, I get dne. All right. And again, if I wanted more detail, I could ask for it. I could say, what's the limit on the left? What's the limit on the right? And maybe we would get more detailed behavior about whether it went up or down. But generally speaking, the general limit as you go towards -4, constant divided by 0 is dne. All right. Now this causes the hole. Yeah. So there is a removable discontinuity at 4. So the hole is at 4 and 1/8. Because the original function has 4 minus 4. So the original function, going back to the original function, if I would have tried to plug in 4, watch what would happen. It's not too surprising. 0 over 0. And that causes that hole. Yeah. I've canceled out the factor. I got a simplified version of the function. Yeah, it's simplified, so that's how I get the 1/8. But I don't actually have a dot at that point. I have a hole or a removable discontinuity at that point. Okay. And then finally, again, this is a very compact question, right? The dne is the VA. All right. So if you're, trying to like pattern recognize, when I do this type of thing and I get this type of result, this is what it means. When you take a limit and you have canceled out a factor, thereby giving you a nice simplified real number, that gives you a hole, right? Because you canceled it. If you didn't cancel these out, then this would have never happened and you wouldn't have the hole. So I like to say the canceling sort of causes the hole. It's one of the reasons why we call it removable. All right. Later on in the next, maybe not the next lecture, but in the next part of the textbook, the end of chapter 1, we'll talk more about what we mean by removable. All right, we'll get into that terminology. So the vertical asymptote is caused by the division by 0. Yeah, constant divided by 0. So that would be -4 for the vertical asymptote. All right, I am running out of time. I guess I'll do one more. We got like 6 minutes left in the class. Modeling this after my in-person version so that you guys, students in the classroom, are getting the same similar experience, I hope. Except you can't ask questions unless you email me. All right, this will be our last example. F of x is x squared minus 7x plus 12 over x squared minus 2x minus 8. Well, we might as well just start right off with factoring before I start taking limits. Now, in this chapter, I typically tell you what limits I want, but how am I figuring out what to ask you? Well, I'm doing this ahead of time. I'm factoring everything. And then I'm deciding after I've factored it what the limits are going to be, what numbers I think are interesting. So let's do the limit as x approaches 3. Let's do the limit as x approaches 4. And let's do the limit as x approaches -2. You see how I'm finding these are called the critical values? These are the values that cause one or more factor to be equal to 0. All right. We can go ahead and cancel this factor and go x minus 3 over x plus 2. And look how nice that is. Now, I do get people will email me. I got one, I think, yesterday. When you get 0 in the numerator, sort of a panic switch goes off, panic button. That's not, don't panic. You don't have, you didn't do anything wrong. 0 divided by 5 is just 0. For this one, the limit as x approaches 4. And again, I will point out that I have already canceled this out. All right, that's why I did the factoring at the beginning. Had I not canceled this out, I would get 0 divided by 0, and then I'd be stuck. You know, what do I do now? It's unresolved. It's indeterminate. But I've already canceled it out. So it's just going to be 4 minus 3 and 4 plus 2, which is 1/6. Not too bad. Nice place to end. And finally, the limit as x approaches -2. Again, I'm using the simplified version. -2 minus 3 over -2 plus 2 is -5 over 0. Now you should panic or calmly exit. It does not exist. All right. And then I want to talk a little bit about these things. All right. This is a point. Yeah, why is it a point? Because it equals a real number and the value exists. Yeah. 3 is a valid number in this function. It does not cause 0 in the denominator. This one is a whole. Yeah. So this one's a solid point. This one's an open hole. Yeah. And then this one is a VA, vertical asymptote. All right. So I can summarize everything. We have a whole, we have a point. On the graph at 3, 0. Yeah. We have a hole in the graph at 4, 1/6. And we have a vertical asymptote at -2. All right. Additionally, we also have an HA, which I didn't ask about previous, or in this problem I haven't mentioned it yet. It is very simple. It's A divided by B. Those are invisible ones. So that's the easiest asymptote. I mean, other than 0, 1. Always give good advice, or my best advice is if you don't know what to guess, 0 and 1 are good guesses in a calculus course. All right. This is an interesting graph now, but just before I press stop, got about a minute to go. And we'll pick up more of this later. Again, not very detailed. This is going to be a very, very quick graph. Very, very quick. And I'm going to exaggerate the scale a little bit. I'm going to say there's 1. There's 2. There's 3, -1, -2, -3. I have an asymptote at -2. I've got a point at 3, 0. That's this point right here. I've got a hole at 4. Oh, shoot. I should have thought that one through a little bit. Here. I'll put 4 over here. Just off the grid a little bit. 4 and then 1/6. So I'm just going to make a mark and call that 1/6. All right. I could be kind of loose with my Y scale here. I've got a horizontal asymptote at 1. Here, let's do 1/6 right about here. Horizontal asymptote at 1. All right. Where's my hole? My hole is right here. It's not a point. And so the graph looks like kind of like this. Yeah, not being very precise. And then there's another piece of the graph right up here. We don't have a super sophisticated graphing system that allows you to plot holes, but I still will show you what they look like. And when the technology catches up with us, we'll see each other someday in the future. But until then, this lesson's over. I'm Dr. Jordan, and I'll see you on the internet.